All right, now let's turn our attention from calculating measures of central tendency and dispersion to actually working with some probabilities. There are a lot of different probability rules to know and be able to use, so I'm going to set up some problems that help us to remember those rules and how to use them. So let's turn to the first one. Suppose you believe that the probability that inflation next year will be below 3% is 0.78 or 78%. Also, the probability that bond yields stay below 6% is 0.90 if inflation is below 3%. So what is the probability that bond yields will be above 6% but inflation is below 3%? So this is a little bit confusing, but let me recap the problem. So you have a probability that inflation will be low, say below 3%. And you also have a probability that says that bond yields will be below 3% if inflation is below 3%. And in the question I'm asking, what is the probability that bond returns will be above 6%, but inflation will be below 3%? So this is kind of a question that somebody who is a bond trader might want to know. Now, if you were following the question closely, you'll notice that I gave you two different kinds of probabilities in the question. The first probability was an unconditional probability, or we could call it a marginal probability. That was a probability that inflation would be low, or below 3%. The second type of probability I gave you was actually a conditional probability. That was a probability of one event happening given that another event was going to happen. So when we are given a conditional probability and a marginal or unconditional probability that are related to each other, we can find the probability of joint events using the multiplication rule. And indeed, as we look down at the slide, I've got the multiplication rule written down, and that is the technique that we have to use to solve this problem. The multiplication rule is a way to find the joint probability from a conditional and a marginal or unconditional probability. So when I say marginal probability, I'm talking about an unconditional probability. So that's often a word that we see associated with unconditional in terms of probability language. So what I'm saying in terms of symbols is the probability of A and B, in other words, the joint probability of both events happening, can be found if you know the probability of A given B and the probability of event B. We just multiply those two together, and this is actually a variation of the definition of conditional probability in the first place. So the definition of conditional probability is joint probability divided by marginal probability, and of course if you rearrange that you get the multiplication rule, which says that the joint probability is equal to the conditional times the marginal probability. So I'll be more explicit about how these things shake out in the next slide, since this might be a little bit confusing since I'm throwing around words like conditional, joint, marginal in rapid fire. We'll slow down and sort it out in the next slide. All right, so let's take a look at the slide. And what I'm going to do, now that I've recognized the problem and I've written down the formula, now I need to assign variables. So my first step is going to say, what is event A? And event A is the thing that I'm interested in finding the joint probability of with event B, but it's also the event that I don't know the unconditional probability of. I only know the conditional probability of that with event B. So event A for me is that the bond rate is greater than 6%. And event B is going to be the event that inflation is below 3%. Now, if I look at those two things, I say that the probability of A given B, or the probability that the bond rate is above 6%, given that inflation is below 3%, is actually equal to 0.1 or 10%. Now, at this point, you might be saying to yourself, what's going on? Didn't you give me the conditional probability being 0.9? Well, I did, but if you look down at the slide, I remind us that the problem gave us the probability of A complement given B. In other words, we were given the probability that bond rates would be below 6% given that inflation was below 3%. So I can always find the probability of A given B if I have the probability of A complement given B, because it's just 1 minus the probability of A complement B. So that's how I got that 0.1. I took the probability, the total probability, which is 1, minus the probability of A complement given B. So in other words, the probability that the bond rate would be below 6% given that inflation is below 3%. And then that gives me the probability that the bond rate would be above 6% given that inflation is below 3%. Because even with conditional probabilities, you know that the sum of all the conditional probabilities based on the same conditioning event, but with the mutually exclusive and exhaustive events of interest, those have to sum up to 1 as well. And I'm going to use that fact here and in other places as well. So if we do the calculations, or I'm sorry, putting in the last probability that we need to know, the unconditional or the marginal probability of that second event, event B, is the probability that inflation will be below 3% in the problem that is given to be 78% or 0.78. So now it's just a matter of plugging and chugging again. And while I'm at it, I might as well give you both probabilities. Since I bothered you with this business about the A complement and A, I might as well give you both probabilities and talk about that a little bit more again. So let's look at the board in which I've written out the calculation. So the probability of A given B is simply 0.1 times 0.78, which is 0.078% or 7.8%. So again, to remind ourselves, this is the probability that bond returns will be above 6%, even though inflation is below 3%. This also means that the probability of A complement B, or the probability that bond returns are below 6%, given that inflation is below 3%, is going to, or yes, given that inflation is below 3%, is 90% times 0.78, which is equal to 0.702. And notice that the sum of the probability, the conditional probabilities here, actually sum up to the probability of event B in a marginal sense. Now I'm going to use a rule like that a little bit later, but I'm just trying to cement these ideas together to show you the connections. And also it's a bit of a reality check because the total probability out there for event B, which is the event that inflation is below 3%, is only 78%. So no matter how you slice and dice that probability by turning it into conditional probabilities, all the probabilities are only going to sum to 78% in an absolute sense. While we're on the subject of this multiplication rule, it's important to remember an exception or a variation of that comes up fairly frequently that some people do find confusing. And if we look at the board, I've got the rule written down that if you remember that if A and B are independent events, then what that means is that the probability of A given B is simply the probability of A, and the probability of B given A is simply the probability of B. That's because independence in a probabilistic sense means that the probability of one event's happening has no effect on the probability of the other events happening. So that way, conditional probability doesn't give you any additional information. So the conditional and the unconditional probabilities are the same. That's what independence really means probabilistically and statistically. Now, some people might be confused with that and uncorrelated and other types of statistical ideas, but for us, independence is really that the probability of event A's occurrence has no effect on the probability of B's occurrence. In this case, then the multiplication rule becomes very easy, and we can see that down below on the chart. I say that the joint probability is simply then the product of the individual unconditional probabilities. And that is, again, comes right out of the multiplication rule because I'm saying that in the case of independence, the probability of A given B is simply the probability of A. So I'm just substituting that into my multiplication rule. And of course, this is only for the case of statistical independence. Very important to remember that. Again, as you write down your formulas and maybe make study aids, you need to write in notes to yourself that say, okay, this is only for the case of independence, or you can just remember this and use the general rule and then use the specific case as you come to it. But in any case, you need to keep these ideas straight because, again, from the perspective of somebody who writes exams, it's very easy for me to give you information about conditional probabilities and then slip in an answer that corresponds to the independence rule. And even if they're not independent, some people might be tricked into believing that that's the right answer. So let's move on to another application of probability rules. Now that we've had some time to think about the multiplication rule, let's pose another problem that uses a different probability rule. Suppose you believe that the probability that the oil price reaches $40 a barrel is 24%. Also, you believe that the probability that natural gas reaches $10 per million BTUs, and that is the standard contract amount when people trade natural gas. They trade it in terms of millions of BTUs or British thermal units. The probability that natural gas reaches $10 per million BTUs is 0.17. And the probability of both happening, which is truly a bummer, so I give it the big unhappy face, is 0.04. So 4% that both things will happen. That would mean that both oil and gas are very, very expensive.